Okay, so let's begin. So welcome back, everybody. So just to do some admin stuff first, today's going to be sort of a hodgepodge day, kind of a transitionary day. We're going to do a little bit of review of everything that we've done so far, and then cover convolutional neural networks a little more carefully than we did in the first day, where I did sort of a rush through demo, and then that will kind of gear us up for the second half of the course. Hard to believe that we're already in the second half. We've been through so much together. And in the second half, we're going to focus kind of, not counting the last week, which is just you guys, we're going to focus, I think, more on basically deep learning stuff, which is kind of the rage these days. And a lot of the stuff that probably got you excited to join up for this course is going to be in that half. So let's just do some admin stuff first. So first of all, this note here, it only gets worse. So basically, first of all, thank you guys. It's been a very fun to kind of make it up as I go. I'm sort of, every week is a little bit of trying to cobble together the things that I think are relevant. It's not very much planned in advance, which I think lets us be a little more flexible, which is kind of a nice way to approach a topic that's so in constant evolution. So thanks for sort of being flexible about that. It's only going to get worse, so so that's my way of warning you. So one other thing, I haven't been taking attendance. I believe that's something I'm supposed to do. Is that correct? Okay, as long as no one, we'll figure it out later. Yeah, I don't know. I can deal with it. Just a reminder, we're doing screencasts. So far, no one's had any issues, but as we get in a little farther along the class, we'll have more. Hopefully, we do have one presentation. Nick is going to talk for a little while for us. And hopefully we'll have more in future weeks. So when we start to have those, maybe you might want to keep your part out. So just let me know. Otherwise, I'm just going to keep on putting these online, and feel free to share them. They're online. I've been telling people who are interested in the topic. So feel free to share them. There, you don't have to ask. Okay, so let's. So I want to discuss office hours. So I've been a little MIA the first 2 days of this week, so apologize for that. What I want to do basically is have one official sort of office hours day, which will be one of Monday, Tuesday, Wednesday, which I want to do a poll right now. And I also want to announce basically I'm going to have more or less unofficial office hours too, because most of this month and next month I'm actually right nearby doing a residency at this place called DBRS Labs, which is it's like a 15-minute walk from here or something. I'll address the unofficial office hours first. So basically, if you feel like showing me a project or talking about some stuff, and it's not during office hours, I'm still free to meet, and I'd be happy to meet with all of you. I'm trying to provide the unofficial office hours, so we don't all feel sort of like we have to get it all in office hours. And I would love to meet with all of you, basically at least once over the next 2 weeks, let's say, and then we can go from there. So that's sort of let's kind of try to pledge that everyone has to make an effort to meet me either at office hours, which we'll determine right now, or the unofficial office hours at DBRS once between now and 4/21. So just keep that. That's an assignment actually. Yeah. And I'll send an email about where it's located and so on. It's a really easy spot to get to. There's conference rooms also, so we can do a lot of fun stuff. And there's people doing machine learning stuff in there, so you might be interested in hanging out more with them. They have residencies and things like that, so that might be something to look out for in the future. And also just gearing up for the final presentations. And I know people also there's the ITP show. And then just a week after that, there's also this, which I want to again plug, which is this sort of art gallery thing that I'm organizing at SFPC, and I'd be super happy if anybody was interested in actually exhibiting something that they made in this class or developing something for it. We should have a whole bunch of like open frame tablets and so on for people to display stuff and printing stuff. It should be really fun either way, so you should definitely think about attending. It's on May 20th, 22nd. So yeah, sorry for the shameless plug, but I'm trying to kind of sweeten the pot, so to speak, for you guys to make something really awesome for the course. And okay, so this is how we'll do the rest of today. So in the beginning of each class, if anyone wants to present something that they either one of their assignments or something that they're working on, just please tell me, and you can even write up to before the class. You can volunteer. So if anyone wants to actually present now after Nick, definitely just volunteer. And just for like five minutes or so, and we'll try to have a little bit of discussion. After that, I'm going to do a little bit more review of the reading stuff that we kind of glossed over last week. Do a review of Wekinator and some of the neural net stuff that we've been, for live performance stuff that we've been covering. Then we're going to get in and then spend most of the rest of the day, probably the second half of today, more or less on convolutional neural networks, which I'll get back to the demos that we saw very briefly in week 1. And I have some new ones also, which hopefully will make a lot more sense. I'll talk about applications and things like that. We'll probably be very quick about showing how to do the applications today, and we'll start to do that more closely next week. I like this sort of repetition, do something really quickly and then a little more drawn out the next week and so on. That kind of helps to make things stick. And then I'll talk about the deep learning landscape in general. Does anyone have any questions on admin stuff or today, or feel like want to volunteer to present? Okay, gonna get you one of these weeks. So have one. So Nick, you want to come up and?
Have it on here?
Oh yeah, I'll just pull it up. You emailed it to me, right?
Yeah.
Oh, okay. All right, let's just record me going into my email. I'll censor this in there. Let's censor this in there. Okay. Is you? Yeah.
It was back. If you go back to your inbox.
Oh.
And then it's the one.
Ah, yes. Okay.
Yeah.
I'll censor this later.
Cool.
Okay. So yeah.
Awesome.
Take it away.
Thanks.
Fine. I'll go switch with you.
Oh, this pulls up my notes. Let's see if I can do this. All right, so maybe a little clunky because I don't have my notes, but that's fine. So with a show of hands, can everyone let me know if you're familiar with the trolley problem? Who knows what the trolley problem is? Okay, small amount. Great, so the trolley problem is a problem in ethical philosophy, and it's a classical problem, and the classical statement sort of goes like this. So you are standing near a train track, you see this trolley, it's a runaway trolley, and it's going down a track, and there's 5 people working on that track. They don't see the trolley coming, and the trolley is going to hit them. You notice that next to you there's a lever. If you pull that lever, it'll switch the track, it'll divert the train, and that train will hit that one person. So the question is, do you pull the lever? If you do nothing, 5 people die. If you pull the lever, 1 person dies. So the question is what do you do? Most people say, in case you're interested, they say, I'll pull the lever. Then the problem gets more complicated. You say, okay, well, what if instead of a lever, you see that there's a very large person standing next to the track, and if you push that person and they fall in front of the trolley, they'll stop it, they'll die, but those 5 people will survive. Most people say they wouldn't do it. So, this is very interesting. It's fascinating, right? It's this sort of thought experiment. But the question becomes, what if instead of a person there, now it's a machine that's making that decision, and you have to program that machine and tell it what to do to make the decision. So I'm going to introduce a word of the day for you all. It's algorithmic morality. So this is just my tentative definition. There's not really an official one. But essentially, it's like we take a value system, we develop a set of principles to determine the right or the good procedure that we're going to give our machine, our computer, when it has to solve a problem. So here's an example of it used in a sentence. And the issue is when you have all of these cars on the road, how are we going to program them to make these choices? So stepping back, Isaac Asimov has this these laws of robotics that he posited back in the 40s, and the first law, if you take a look, it says a robot may not injure a human being or through an action allow a human being to come to harm. So if we think about this trolley problem, essentially the robot is in this catch-22 because either way, whatever decision it makes, it's going to hurt somebody. Somebody's going to die. So, when you take something and you say, well, what if the way that people are framing this in this conversation around driverless cars is, what if the car is on a mountain road and a school bus is coming down and it's full of children? What should you program the car to do? Should the car, when it sees that school bus and knows that it's full of children, should it drive off the edge with you as the driver in it? Or should it, keep driving ahead? Or what should it do to deal with that situation? And the thing is, when, this traditionally in ethical philosophy, this is sort of a thought experiment, right? It's a way that we think about, well, how do we define murder? Where do we place our value, in individual human life or in group survival? But when we're talking about programming autonomous machines, someone actually has to decide, and there has to be a decision about exactly what that machine is going to do. So this gets even more complicated when you think, well, okay, what if we say, not only is it about going down the hill and do we take children or a machine, which is something that, when we start to make those decisions, we have a really hard time saying, if there's no human agent in that. But then what if instead of, you in one car and a group of kids in the other car, what if there's a car and it has 5 people in them, trigger warning, what if they're all like rapists or they're all mass murderers, and the car can know that, because it knows who's driving it, and then the other one is a scientist who's on their way. They've just come up with a cure for cancer. They're on their way to give a talk. What if Google or whoever is running the cars has access to that data? Do we give it the authority, and what choice do we tell it to make in that situation? So. The place that we find ourselves in right now is that we're sort of screwed when it comes to making these decisions because we don't have the right hardware and we also don't have the right software or the right thinking to actually decide, figure out how to solve these really complex problems. So in the meantime, as these cars. As these sorts of autonomous cars and autonomous machines in general become more prevalent, like a lot of mistakes are going to be made and things are going to go wrong. But potentially down the road we will have better solutions. So some people have suggested, well, what if we can just sidestep these issues, and what if we develop an algorithm so that you never even get to the decision? So for instance, back to the mountain, what if when the car knows it far enough ahead of time that the bus is out of control, it tells you as the passenger, get out of the car, get to safety, and it just sacrifices itself. And so then no one is harmed because the car just passes by, right? So this is a potential solution that is suggested in the future. Another thing, pulling back, is maybe there are one or more bigger pictures that actually make this whole question of sort of the trolley problem for driverless cars moot. And that is, even if we have to, as people who are programming these machines, we have to program it to make these really difficult decisions. Even if that's true, statistically, driverless cars are still going to be safer than still having us as humans driving cars. So some people are saying, why are we even having this conversation? And by the way, this is like a very big conversation. If you just type in driverless cars trolley problem, you'll get like 1 million different articles that are written about this. And so, the bottom line is actually, as with the advance of this sort of technology, ultimately we're most likely going to be safer, at least in terms of like vehicle-related deaths. In closing, if anybody I'll send out some stuff, but if anybody wants more to dig into this more, there's a lot of interesting stuff. For instance, I didn't even touch on this, but there's the question of like, who has control of the code and makes those decisions? So not just thinking about like, what do we want those decisions to make, but like, who's in charge of those decisions, not just what are the decisions that we make. So that's a really interesting kind of train to go down. So anyway, thank you guys.
Does anyone have any commentary?
I was thinking about Wekinator and stuff like that. That lets you kind of abstract even more. Like you're not explicitly coding something, but you're kind of giving it like models to interpolate from. So like I don't know, imagine like giving it one thing where like some really bad event where tons of people die and like that happens if something happens that looks like this, do this and then do something else.
Sure, we can swap out different value systems.
Yeah.
And this is it's like much more general than just driving. Any sort of automated systems, there are value judgments that have to be made, and it's not at all obvious.
I just heard this morning in the radio something about that. I'm from Austria, and there they have like problems with giving credits. Like they have the discussion about giving banks giving credits to people because they would not give credit to a teacher, a female teacher, 35, whose name is Fatima something, and even though she has the same income than another man whose name is very German living in that thing. So, and this is also like the outcome of machine learning, right? They just associate with foreign names, problem and like related to whatever, terrorism, whatever. And so like this question of moral, I think, is very interesting. Can we really leave our machines to do decisions that are obviously not based on numbers exclusively? So.
Well, and that's something too, is like this notion that the machine is always going to obey the rules, and like in the traffic situation, actually sometimes you don't obey the rules because, or like if you're merging onto the highway and everybody's speeding, then it actually doesn't make sense for you to go at the speed limit because you'll be in danger. So, but the car is not going to know that because necessarily, unless we program it that way and say modulate based on speed, but then it just gets more and more complex. So,
I think the idea of like liability is what's most interesting in these cases, because like even if we did reduce like from 1 million deaths to 100,000 deaths, it's like there's still death because of like decision making and who's liable for that.
Yeah.
Like the car itself, like the people that coded it, the company that has it,
the owner.
And like it was interesting. I was listening to like an NPR segment that was talking about when like Google Photos was doing like automatic like labeling. When it first came out, there was like 2 Asian Americans where him and all of his friends and their photos got labeled as gorillas. And so like really racially problematic. And like at the same time it's like the code that's making decisions on this, but then you have like inherent bias in the code probably because it's probably predominantly like white males making the code, and then where does the liability fall in of like whose fault is this, and like how did this happen?
Right.
Anybody else? Thanks, Nick. Okay.
Morality.
Okay, thanks, Nick. So I'm gonna volunteer another very quick. I'm gonna do this kind of quickly, and then we'll get back into the application part. So I was looking up some quotes by Rene Descartes. So everyone knows Descartes invented Cartesian coordinates and basically like algebraic or not algebraic, but f of x notation, functional notation. So Descartes was very well known for being a dualist, which means that he thought that mind and matter were two separate entities. So like the mind is the soul and it's immaterial, it has no matter, and it's totally separate from the body, and the body is like what we think of as a machine. And he basically said that animals are machines. So he actually wrote this. He literally wrote animals are machines, and where he basically said that animals, or brutes as he called them, or beasts or whatever, they have bodies, and a lot of them are very good bodies. Like they're good at doing things that maybe humans aren't good at. But because they cannot speak human language, they don't have the same. They're categorically separate. They're like matter, and then only humans have minds, and so therefore you can abuse animals because they don't actually feel pain. So they don't have rationality or intellect. And he was like a surgeon and all this stuff, and they practiced vivisection, which means doing live dissection on animals. So like to open them up with their beating hearts. I'm really sorry to bring that in. But the reason why I bring it up is to note that in the past, it was the case that not everyone necessarily looked at animals and thought of them as sentient beings like humans. And right now we're in a situation where we look at machines and we don't necessarily think of them as sentient, and I think almost probably nobody here has as much empathy for them as they do for animals. But if you could imagine in the future, if the way we came to empathize with animals is by observing them behave a lot like us, that's really where it came from. Like when you look at germs, you don't, or you can't see germs, ants, let's say, you don't empathize as much with them because they don't seem to exhibit the same, recoiling from fear or,
Maybe they do and they're just too small.
Maybe, yeah, it's very true. Yeah, who knows? And so when the robots begin to demonstrate more of these capacities that we empathize with, are we going to start to think of like the notion of mistreating robots themselves? So that's all something to think about. Yeah. Anyone have any? Did anyone see District 9? I keep thinking of that when I look at this. So yeah, Descartes, what a monster, right? Okay, so just in general, for the next few weeks, like if you, including next week, if you want to volunteer to either talk about something interesting that you read or to demonstrate an application, more or less anything relevant to this course, just please email me and volunteer, and you'll have some time to and it doesn't have to be recorded. It's just like that's optional. Okay. Then, so yeah, in the notes I included a few more links that you may want to look at. There's a lot of really good writing on like notions of bias, ownership, and privacy, which are all things that are, I think these links are, I'll have to fix these links, but basically you can see that one is going to a Nature magazine article. There's a Reddit AMI with some like ethicists who have a lot more. They think about this stuff on a basically daily basis, so there's a lot of really interesting stuff. And this is just a big list of reading that's categorized in different things, so this is also something that's worth looking into. I've only looked at it briefly. Okay, so let's get back to the application-based material. So I want to do just a bit more of Wekinator. I made a couple of new little applications that we can demonstrate today, and one that we failed to demonstrate last time, which was using Ableton, and I know why. It was a stupid reason. We'll demonstrate it today. And then we'll get into convolutional nets. So, yeah. Any questions? Anybody? Okay. So let's get back to Wekinator. So I'll just do a really quick, like a super quick review just to remember how the interface works. So like when you open up Wekinator, and I'm going to do this quickly because we have this all in lectures before, but again, a couple of the things that we didn't really look at last time is actually these options can be very relevant. So for example, if you're doing classification, so if at the default, it just gives you a bunch of continuous values, right? But if you're doing classification, you can change to classifiers, which just gives you binary outputs. So that's worth knowing. And then you can also, instead of, if you want to have some of each, you can do custom. And then you just go into configure. And then however many outputs that you have, like let's say, you just go configure. And then basically each one gives you all of the options. So like, do you want a numerics or continuous, real valued? Or a classification, so that's binary or multi-class, and you can also here we didn't do this before, but by default it goes from 0 to 1, but you can make the bounds however you want. I usually do the sort of rescaling on whatever application is either sending or receiving from Wekinator. So I usually just leave it at 01, but maybe you might want to change that, especially if you don't have access to the application that you're sending to. And then soft limits, hard limits means that soft means it can actually go less than 0 or more than 1 if the actual, like you train it on continuous values between 0 and 1, but then depending on how the inputs come out, it might actually make a classification, or it might actually regress beyond that. But you can choose to cap it if you want. Again, these are all things that you can take care of on the application side as well. You can also, instead of using a neural network, you could just use a linear or a polynomial regression. You probably won't need to mess with that too much, especially if linear polynomial regression is a little simpler, and but for the most part, we can kind of ignore that. Okay, so. And we saw, so in the last lecture, we saw like, okay, you can send in some inputs like the mouse, for example. That's 2 dimensions of inputs. And then we had it going into some sort of an application that we would learn on those 2 values, some classifier or regressor, and then use that to control another patch. So I'm going to show you a couple, just more interesting, hopefully. These are super untested, so this might be a bit of a struggle, but hopefully we can kind of make it work. So what I wanted to do is last week I tried to show you Ableton, and I know that not too many of you use Ableton, so I'm just going to do this really quickly just to demonstrate the idea of like controlling audio, and I'm going to show you another way to do it, which is using audio units. So I'm going to load up Ableton. I'm not a big Ableton user myself, but basically I have this application called Ableton OSC. The reason why it wasn't working last time was because I think the port was occupied. But this is what should happen if you download this application. So I made this application. You can download it. The link is here. So it's just. So
I did it, but it doesn't work.
It doesn't work. Okay. Oh, did you install Live OSC?
Yeah.
Okay. Well, let's talk about it after class, or yeah, because it's probably something straightforward.
It's different things.
This is always, little things. Ableton doesn't do OSC by default, so it's a bit of a hack program to begin with. But anyway, the way this interface works is it gives you, so I have it set up by default to just plug straight into Wekinator. So you see there's the address it's looking for and the port. And then basically here, it lets you just select the parameters that you want. So I'm just going to really quickly like make a super fast set. Which is the same one that I do in basically every demo that I've ever done with Ableton, because I don't use it that much. So I'm gonna put in where's my favorite tabla? Yeah, here we go. Oh, you put it here. I think I did this last week, right? Okay. So let's say, and let's just put in like some house music too. All right. So you can all hear that, sort of. So let's put in. I'm also gonna put in like an effect that we can, and I'll put it on the master track. So the effect will use this like resonator. Okay. Nice, right? Oh, that's right. Yeah, let's plug in the audio. Okay. Yeah. All right. Now we're talking. So, what was I doing? Oh yeah. So actually, I should just restart Ableton because Ableton OC. So now if I do this, it will pull up all of the tracks. So if you see, like I go into the master track and it has my Los Angeles, the Los Angeles resonator. So for example, we can choose to like, okay, let's say I wanted to change the dry wet. I would just select this right here, dry wet. And now I have it as a slider in Open Frameworks. Okay, so I have access to it there, and I also have it controlled. Now it's also controlled via Wekinator. So if I go here, if we just go simply, let's just do continuous, and we'll do 1. I think this should work, I hope. So if there we go. So you see now we're controlling it via Wekinator. And maybe we can control, like, we can put in a few more. So like the global parameters, like is tempo. So I put in tempo, okay? We don't want to go that fast. And then maybe like, what else can we do? Anybody use Ableton more than me that has a, I think the decay sometimes is interesting. It's like, sorry? A filter? Oh, like another filter? Oh, like the frequency of the filter. Oh, that's right, yeah. Doesn't that do much, right? Maybe, the pitch, maybe? That's kind of ugly, but I think I broke it. It had a color? Where's color? Bottom left. That's perfect. Okay, let me actually remove this and just go back to the default because it sounds better. And then color. Yeah. So go to color right there. Cool. Okay, so let's learn on these 3. So I'll go back to Wekinator. And now let's decide on what we want to use to control it. So our options are sort of limited because I don't have a Kinect here, so maybe we'll just use Face OSC again. Okay, so let's do that. Okay, so Face OSC, if you recall, so let's just set this up. I'm gonna close this, open up Wekinator. So we're gonna have 3 outputs. They're gonna be continuous, and then our inputs is gonna be, I think is, actually, hang on, Face OSC. Okay, cool. So we're sending, I think what was it, 132? Yeah, 132 inputs, start listening. And, 140, right, I'll turn these off. And receive 140. Okay, still something wrong. It's actually 140, that's fine, so I'll just change it. And go. Okay, it's working. So now let's train on like, let's do like a few different like classes basically. So let's say we want okay, so that's super wet, right? and then this is, oh, that's really fast. Okay, so we'll do like fast, wet, and high color. And we'll do it like if I sort of turn my head to the left. Let's try to remember these this time. Didn't really. Okay. Face. And what? Oh. How did I get 140 before? I must have pulled up the wrong one. Was it right? I'm 32. Start listening. Okay. Raw is going in. What is happening? There is something. How did we do this before? So we had sort of this. Let's do slow and a high color. Okay, so that's one. So now I think we're ready to record, right? So let's say like when I do this and put my mouth open, we'll record these. Okay, good. Now let's make like a dry example. That's kind of fast. Maybe not that fast. How's that? And maybe middle tone color. And that will be if I do... Go ahead. Pull my mouth to the side. Yeah, let's do that. Good. That should be enough, actually. So let's train that. Because basically, however many examples you give it, it'll find some interpolation of the space that makes sense to it. Maybe we can probably give it some more, but... Okay, so because it has a vector of 132 inputs, it might take a little while to train, so you can see that it's going through each of the three. It trains them all individually. And so it trains an individual neural network on each of these bars, however we happen to set it up. And it's gone through one. And just to review while it's doing this, like as soon as it's done, we'll have this, the run button will be ready to enable, and then it will just begin to, as we send inputs from face tracker, it will then do regression on each of these three parameters. So it's done two of them now. And also it's worth noting, I guess I didn't mention this last time, it doesn't classify necessarily continuously, it just classifies every time it receives a new input. So because face tracker is sending every frame, it appears to be continuous, but if you set up your application to send inputs only once every however so often, it will just classify whenever it receives a new one. So that's kind of worth noting. Okay, so if we run this now, okay, so like, how do I do it before? Remember that was the first class that we trained. So you get the basic idea. Yeah, it's a lot of fun. You could probably do a lot better by just like by having a few more different trainable classes, but because we just have two, but you know, in principle, it's up for you to experiment. I'm just gonna stop Ableton. another thing to know is that you can actually save projects. So if you go to in the Wekinator menu, you click Save Project As, it will save basically the entire project, including the trained model. So like if you come up with something you like, you just save it, and then you can load it. It has the model in there, and you pipe the same inputs to it, and it will then remember the classifier that you trained before, which is really nice because sometimes you might be training super complex models, and you don't want to keep retraining it, before you have to use it. So that's something to know about, and that's Ableton. So if anyone wants to use Ableton and wants to use this tool, is having any trouble with it, just let me know, and I can definitely help you. I'll show you one other quick thing. Is another application called that I actually just finished basically yesterday. So it's not quite done. This is super rough, but it's just in case anyone uses audio, in case anyone here is a musician and uses audio units, or like those are like VSTs for Mac. Again, this is only Mac, so apologies for anyone using Windows. But basically, if you can use, and I'm going to put this online later today, I just have to finish it. It basically works exactly like Ableton, except it uses audio units instead. So I've got this audio unit called, let me just get out of this. This audio unit called Alto. It's like, which is a really, really awesome synthesizer. And basically, like if you can, I'm just going to cover this really quickly, but basically if you go to like, let's say one of these presets, this is one that just happens to work, it's a MIDI device, so like you can send it notes, but this preset just has it uses a sequencer. I'm not going to cover Alto because it's not part of the course, but just to show you that if you do use audio units, this works exactly the same way. So it gives you all of the addressable parameters. So for example, filter cutoff, if I click on filter cutoff, I can now control this is filter cutoff. I can control it via Wekinator. So now if I open Wekinator, okay, so that might sound horrible, but you get the idea. I just wanted to show that really quickly so that you're aware of the tool being there. I'm going to put it online after this course. So if anyone uses audio units, definitely that's a nice way to bridge between Wekinator and different audio units. I have it hard-coded for Alto, but I'll make a menu that lets you. If anyone is interested in using this, then I have a good reason to hurry up development on the tool. So, so just let me know if you have any interest. Okay, let's go back to the notes. So that was Ableton and audio units. Let's see, this 410. Okay. Oh, and I had one more that I wanted to really quickly show. Let's let's go back to using. Let's do another audio input example. So I'm going to open Wekinator. So this is, I'm going to show you, I just coded this up. This is something I made years ago, but I kind of found it again today. So how many people here use Maximus P? Okay, lots of people, good. Okay, so for those of you who are interested in using Maximus P, I'm going to demonstrate a really quick like Max application. So this is like this patch that a friend of mine showed me a few years ago. That's like the super simplest, coolest thing you can do in Jitter ever, I think, is like load a movie. So I'm just going to find like, okay, here's a movie. There's some train in Germany. And then if you start playing it, this is what's going on. I'm just going to make this a bit smaller so you can see it. So this patches kind of effect. What's going on is, I'll show you the movie itself. It looks like this. It's just like a YouTube video of someone riding a train in Germany. And basically what you do here is you read the movie out, and then it goes into a jitter matrix, and then we're doing a basically a cross multiply, right? So it's like I take a single what is it? I take the first, I already forgot actually what's going on. I think this takes the first row of the video, and then what's it doing? It basically takes a vector from the video of pixels and then transposes it, and then so you have two vectors, one is transposed, and then you cross multiply them, right? So if you multiply for those who remember linear algebra, if you take like a column vector and multiply it by a row vector, it'll give you a full matrix, and it looks like this. So it's kind of a neat little, really super simple, cool thing you can do with Jitter. But a really neat thing that you can do with this is if I stop the metronome and I just have it here, we can actually control this with like a position cursor. So if I go here, and this will play back basically between 0 and 1. Right, so I can control playback like this. So that's another way to control playback. It can get a little locked up. I think it works best with short videos maybe. So it might be better to like do a short video. But let's just use this as an example. So knowing that, we can, this is already working. So I'll start listening, and I'll just, to demonstrate, this should just work. It does, yeah. Okay, so let's make a cool example of this. So suppose we want to go back to that that bark analyzer, which is also in Max. So we can have two separate Max patches. This patch right here is going to control this patch. So this one comes with Wekinator, and it just extracts bark coefficients, and it sends 25 inputs to Wekinator. So I'm going to open up Wekinator. We'll have 25 inputs and just one output, which is going to be continuous. Okay, so now let's train it, and I'll just train it on like a couple of short sounds, and hopefully I'll find some that aren't embarrassing. So I think that's picking up. So let's associate it with 0, just like this. Ooh, okay, and I'll associate it with like up here. E. How about that? E. Okay, cool. So now I'll hit train, and it's running. Okay, so now I'll go ooh, ee, ooh, ee. Okay, so I sound really silly, I suppose, but you can see what's going on. If you do this a lot more carefully, like if you spend more than 2 minutes, like I just did, you'll probably come up with something that behaves a little more interestingly. Or maybe you might want to smooth this. So there's ways you could smooth it. You could apply like some easing to it. Ooh, you probably should have had it. Probably should have trained it like 0.1 instead of 0, because that's all black space. E. Okay, so that's the basic idea. I think it would work a lot better with a short sample. That's what I suspect. But this is just a little short, quick example of doing like audio-reactive machine learned visuals. So that's cool. Yeah.
If you wanted Wekinator to, I guess I'm thinking about like if you had like a persistent sound, or if you wanted it to recognize like how sound is changing over time, is there a relatively easy way of doing that, or is that?
When you say sound changing over time, you mean like its features, sort of like how, like you want derivatives or something, or?
Well, so the case I'm thinking about specifically is I'm working on a separate project where I'm trying to detect like car horns. So for that, I was looking for like loud frequencies that persist over a couple of frames. So I was curious, is there a way to feed that kind of information into Wekinator? Like,
yeah, absolutely. I mean, you'd have to. You'd probably need some software that does that grabs the features that you're specifically looking for. One thing you could try to do is if you're trying to make a classifier which detects car horns, is to actually train it on, you could look for these, like you could use Bark, the Bark or MFCCs. There's also an example that comes with Wekinator that does MFCCs. These are all different audio features, so I don't expect people to know what these are. These are just like if you do audio stuff, you might come in contact with these. There are different features that are extracted from audio, and so you could give it a whole bunch of examples of car horns that are attached to a positive class label, and with these features extracted, and then you could give it some other examples of non-car horns, which have the 0 class label associated with them, and then you can train a car horn classifier. That would probably work reasonably well. Is that what you mean? Like you wanted to detect car horns?
Yeah, exactly.
I think you could do it that way. It may not be super accurate. Doing like sound classification is somewhat less developed than like image classification these days, but people do that, and it's certainly worth trying. Okay. Okay, so let's see here. We are okay. So that's basically like what I wanted to kind of do with Wekinator. Raise your hand if you're thinking about using Wekinator for either this course's project or just in general. Okay, lots of people, lots of interest in Wekinator. So in that case, like if people continue to work on Wekinator stuff, we could continue devoting some more class time to it. And also, like if you're developing projects and you already have one in mind, please email me and let me know. Definitely, like would love to see some more Wekinator work. Super easy way to sort of bootstrap some machine learning into some already developed work that you might already have. And so yeah, and if you have an application that you want to use with Wekinator, but it's not clear to you maybe how to hook it up via OSC, also just let me know because I might know. A lot of things accept OSC natively, but then like for something like Ableton, for example, I had to hack it. So there's usually a way if you look close enough. So just let me know what you're thinking, and there's all sorts of like novel applications which are worth looking into, and definitely check out. This was covered last week, but the materials that are posted by Rebecca and other people using Wekinator and the classes are also going to be useful to you. Okay, I'll do one more quick thing before getting into Convnets, which is just to talk about a few things that are available. Again, we're not going to, I just want you to be aware of what's there. We're not actually going to look so much at how these are being done. Unless people become interested in it, then we'll look at it more closely in the following weeks. And then we'll take a break we'll probably just do an early break today, and then we'll go into Convnets. For those of you who are interested in doing, I've gotten a few emails, not just from people here, but also from people just more generally interested in the material, who are interested in doing stuff with the Kinect. You can do pretty decent like gesture recognition and pose recognition in the Kinect. And actually, like the two demos, the few audio demos that we just did right now, where I used Face OSC, we could have easily done the exact same thing with the Kinect. Just swap in the Kinect skeleton features for the face features. I just only use face because it was easy to set up. But with the Kinect, because I have this Kinect OSC, which is nice, and there's also other things like it that just pipe Kinect data over OSC. It's pretty easy to get Kinect data into Wekinator, or you can also just use some software that I've made specifically for Kinect that you might find useful as well. It's just a question of preference. So like you might with the Kinect with Wekinator, it's a little bit easier to get started. But if you're using open frameworks and you're interested in doing stuff that also has some other open frameworks components to it, you might find these useful. And also because they're tools that I've developed, that's also a good reason to use it, because then I can help you develop it further. It's a good excuse, basically, to develop these tools more. I made a really quick, and I'm not going to demonstrate it because we don't have a Kinect, but basically you can do. I made an interface that lets you train. Actually, maybe we can do a quick. Yeah, let's do this. I'm just going to show you. You can actually do a. This might not be worth looking into very much, but I'm going to load with OpenNI. You can actually load like pre-recorded videos. So this is an application I have. It's not online yet, but for anyone who's interested in using it, basically it tracks the skeleton features of a Kinect. That's me from like 2 years ago. And then you can, let's put me out of the way. And then basically there's an interface that lets you choose classes. So you could say, like, in very much the same style as Kinect, you would hit the keyboard and go, I want this to be class 1. And then you start recording, and then you'll have some pose. So let's say you make a T pose or something like this. You can associate that with class 1, record a bunch of examples, just the same way as Wekinator. And you can give it as many classes as you want. And then you can, this basically works exactly like Wekinator, except it doesn't have as polished of an interface. But it's nice because it's within open frameworks. So if you want to use some open frameworks libraries, if you don't want to use open frameworks, you can more or less accomplish the same thing with Wekinator. So there's not necessarily much reason to use this. But in case you're interested in doing some stuff with OF, just be aware of this tool. I have a variant of this tool, which called Connect to Gesture, and I actually showed it very briefly. You can download this. There is a maybe there's not a release. Let me know if you want to use this, but basically if this works pretty much the same way, except what this does is instead of classifying poses that are frozen in time, this actually has a metronome and it classifies a gesture, so a movement between 2 points. So like a metronome will come on, go on, and then you do a gesture. So like let's say you do a hand wave, and you want to associate that with a class. So this is class 1. You would give it a whole bunch of examples, and you would do this for as many classes as you want, and then you have a gesture recognizer. So that recognizes time-based gestures. And I have a demo also of this that's online. So in case, for those of you who are interested, a few people have asked about gesture recognition, so this is also something worth using. The demo tutorial video, you can see right here.
This tutorial will show you how to use Kinect.
And we're basically like, this explains how to use the software we were just looking at. We don't see anything because there's no Kinect, so nothing's detected. But basically, this is how it works. You give it a whole bunch of classes, and then it will predict classes. And then it outputs them over OSC, again, similar to Wekinator. This is one thing that I think would be kind of a little more difficult for you to use Wekinator because there's no built-in sort of metronome type like feature. So one problem with gesture recognition is deciding when a gesture starts and stops, right? Because it's not clear what is the gesture that you want to classify.
To run the Kinect.
Begin to record gestures within the space. So that's one issue that isn't built into Wekinator. So if you want to do sort of something kind of musical or timed to a metronome or a beat, this is how it works as a training process.
And you can see that at the end,
so you just give it a whole bunch of them in the space of the red light.
In the space of the red light, and at the
and
end,
then you train it later, and then
generate a feature vector and add it to this
effectively recognize
spreadsheet
classes.
with the label
Okay, so
1.
this is just to be aware of, and I'm not going to do a full tutorial today because I'm not sure if anyone actually wants to use it. But in case people are interested, maybe if you want to look into this, please talk to me. Maybe during the office hours or email me, and then I can tell you a bit more details about some of the things you can do with it. In case you're interested, like what we did with this is a project that I did with some collaborators. Was we basically made an application that wrote Arduino code from gestures. So this would be void setup. You would do something like that, right? And it was actually communicating with an Arduino, which so yeah, we would basically send the gestures. It would create code statements, and then we basically recreated the whole Blinky script for Arduino, and then ran it on an actual big set of light bulbs that was connected to an Arduino. So it's a nice little like, if in the way you can see that like it's with this, just like Wekinator, it's agnostic to what it's going to, so you can really like control anything. So if you have some pre-existing artworks that you can imagine different ways of controlling, this could be you could think of this as a sort of way to control existing artworks that you have. Okay, so yeah, that's Kinect to gesture. Let me know if you're interested. All of this is online, of course, so you can also look at that. Someone mentioned to me actually also OFX GRT, and I haven't used this myself. So for those of you who are using open frameworks and you're interested in gesture recognition, there is a wrapper for probably much better gesture recognition software than mine, called Gesture Recognition Toolkit. However, I haven't used this, so I don't really know how good it is. But it's worth looking into again if you're interested in doing gesture stuff. Okay, any questions? Okay. So here's what we'll do now. Let's do our quick break now, and then when we get back, I will begin convolutional neural networks, and we'll cover them in a little more detail. And we're not really going to do too much more. We'll see how things go, but mostly just what I want to prioritize today is for everyone to understand how convolutional neural networks work, what they are and what they do. And then to the extent that we have time, we can get into some applications, but we'll probably do more coding and applications starting next week. Okay, so yeah, let's take a break. In the second half of the course today, we're going to get back to convolutional neural networks, or more or less introduce them. In the first class, when I did a very deep dive of the, what we called the whole course in 1 hour, I talked about these for maybe like 15 minutes or something like that. And so some of the stuff we saw very briefly, some of the demos, and I have a couple of new ones as well. But what I'd like to do is kind of like talk about what convolutional neural networks are, how they work, what they do differently from ordinary neural networks that we've seen, what the advantages are, and then we'll kind of start to look at what some interesting applications of them are and why they're so exciting these days for different applications. And that will be more, I think we'll spend most of the last half of today doing that. And then depending on how much time we have, we might do kind of a cursory look at some of the deep learning software that exists out there that we're going to probably begin to cover in a little more detail next week, I hope, which will start to get a lot messier and a lot more experimental, and maybe a lot more fun. So we'll see how that goes. But today we'll kind of like, let's talk about Convnets from a high-level perspective. So before showing Convnets themselves, let's talk about the limitations of ordinary neural networks and how they sort of fail. So we've already seen, I showed you this in the first day. There's a demo of actually, let's look at MNIST first. So when we apply an ordinary neural network to, actually this demo's wrong because this is actually using a convolutional neural network, but yes, this won't make sense. This is actually running a convolutional neural network. If this were an ordinary neural network, the accuracy would be much less than this. This is getting around 60%, which I think might be overfitting a little bit. But with an ordinary neural network, I think it would be like maybe 20-something%. And the reason is, and that's not that good. That may sound great for 10 classes, but remember that random guesses would give you a 10% accuracy. So that's not actually much better. So yeah, ordinary neural networks start to behave really badly with complicated classes like this. So now why why do these neural networks, okay, so we look at, these are cats that are correctly classified as cats, right? If we look at cats that were misclassified as birds, it may not be obvious to us why the machine thought it was a bird, but it should be pretty apparent why, why these are wrong to why they're misclassified. And the broadest reason is that there's a lot of diversity in these images of cats, right? So like, we picked a very easy problem to start neural networks with, that's classifying handwritten digits, because there's a lot of homogeneity among the way that they appear, these images, right? So it's kind of easy to train a neural network to classify handwritten digits because they appear in a very similar way across all the samples that we get. So this will be a little easier to demonstrate if we look at the weights. So I have another demo that shows that. Oh, is it broken? Great. I have one that is going to be working. I hope. Yeah. Okay, so if we look at recall, this is an ordinary neural network, right? And if we let the weights evolve, and we looked at this briefly before, but basically, you recall what these are, right? These are grayscale images of where the pixel refers to a single weight, each of these pixels. So for example, in this 0 weight, this connection right here, the strength of it is denoted by that pixel. And so these weight images are basically like templates. Or that's kind of how we end up interpreting them. Like most zeros, if you sort of average them out, they look a bit like this, right? And so the weight, and so this neuron right here will have a very high classification if the image it receives, these pixels, line up very well with the weights. So if we get an image of a 0, we expect that the high values, where it appears to be white, will mostly line up with this weights image. And so high values will get multiplied by high values and give you even higher values. Low values will be multiplied by low values and not contribute much to the score. But because those, they would have a high correlation in theory, the 0 neuron would have a high score when it receives an image of a 0, whereas the other weights should receive a lower score because they don't line up as well. Does this kind of make sense? Like this notion of a template and multiplication? So it's, and this is true for all of the classes, right? Not just zeros. Yeah, that's more or less what weights are trying to do. Now this is a one-layer neural network, so there's no hidden layers. So basically we force this network to learn these templates in the first layer. If we have hidden layers, that creates an opportunity to do things a little differently, and we're going to get to that in a second. Let me just look back at the notes, make sure I have. Right, actually, okay. So I was gonna kind of toss this up. So a toss-up question. So these neural networks that we're looking at right now, how do they deal with translations and stretches? So like zeros appear in different sizes. People might curve them differently. Some might have very long zeros, some might have very wide zeros, and so on. Is it evident from these weights how neural networks try to account for different kinds of zeros? Someone want to take a stab at it?
I mean, I think the fact that there are white pixels around the most widest area, it means that there's a possibility that someone is drawing bigger zeros than like the most usual one.
Mm-hmm.
And I think that's also like it gives like possibility of different varieties of zeros.
Exactly, yeah. it's drawing wider here
Yeah.
because it recognizes that some zeros might kind of appear on different parts of it, right? So some zeros might be on the outer edge of this, and some might be on the inner edge. And so it's almost like an average. Yeah. But it doesn't want to give too much, right? Because if it goes, okay, well, zeros can be all around here, then it will be a wash with all these other classes. So it kind of tries to it's trying to maximize the accuracy, right? So it's the loss function that trains the network is telling it just adjust yourself so as to get the highest accuracy possible. And that's how it does it. So yeah, that's how regular neural nets deal with it. Now, if we look at this more complicated data set, the CIFAR data set, and it gets a much... my demo for this is actually broken. I wanted to show the CIFAR weights, but the demo is not working because of the color. What I'll show you is actually an image that is already produced that will give us a hint of how it works. So this is just going back to the presentation slides that have some of the demos in there. Okay, so Convnets. Okay, so like the weights for CIFAR 10 would look kind of like this. Now technically this is not actually produced using a neural network. This is produced using just an even simpler, just a simple linear classifier. But it would work basically the same way if we produced this with a neural network. And this is from, for those of you who become interested in neural networks specifically, and especially convolutional neural networks, this is a course there's a MOOC that has been just run at Stanford at the computer vision department, just finished. And it's a really, really good class. So for those of you who are interested in taking this further, I definitely recommend looking at this class. But if we look at the weights for CIFAR 10, you'll see that they're much less defined than the numbers. Obviously, they have color, so that's already makes things more complicated. It makes things more complicated in a sort of simple way. The way we deal with color is just by tripling the number of neurons and then interpreting all of the red, green, and blue values as separate pixels, basically. So color and grayscale really work basically the same way. However, with color, you just have a lot more data. And because there's a lot more data, you need a lot more data, or you need a lot more samples to give you a sense of how that data works. And obviously, color screws things up because, like, suppose that we were dealing with color images of handwritten digits, and you could have green 2s and green and red 2s. You would basically, like, the approach we had before, you would have to take that into account. We didn't have to do that with MNIST. We just have high and low. But with color, you have to take that into account somehow. Now, the way that it ends up working with these CIFAR classes, and actually I haven't shown you I should show you a slide from what they look like. This is a data set that's used a lot in machine learning that contains these classes: airplanes, automobiles, birds, cats, deer, dogs, frogs, horses, ships, and trucks. And it just contains samples collected, I think, from the internet. So here's airplanes, automobiles. And right away, it's apparent how much diversity, right? We're looking at images of cats here, let's say. And, some of these cats are indoors, some of them are outdoors, some of them appear at different angles. They might have an overhead angle. Some of them are outstretched. Some of them are curled up. The cats have different colors. There might be other things in the image too. So that's another problem, right? So we're dealing with clutter. So these are much more difficult to classify now as than handwritten digits. And that's important because this is a much more real-world task. Usually we're dealing with handwritten digit recognition is a real-world problem, but most problems are much more difficult. So that handwritten digits is kind of a nice one. We cherry-picked it because it's easy, but this turns out to be much more difficult. And if you look at the weights, you can kind of see what's going on, right? So like the best it can do is these sort of blobs. So like a lot of images of deer are outside. There tends to be a lot of grass and trees. And so there's a lot of green around the perimeter and sort of a brown dot for deer. So this is kind of the best it does. It just tries to match this template, and it should score a reasonably high amount for a lot of deer because there will be a lot of green on the outside and there will be some brown object in the middle, right? But it won't usually, but obviously this will overlap with a lot of different other classes, and so it'll tend not to work very well. You can kind of see with the others, some of them are more obvious than others. So like with the car, you see that there's like kind of a windshield here, and it's like the car facing forward. Plane, it's just mostly a blob of blue. Planes and ships get confused a lot because planes appear in the sky and ships appear in water. So those are both blue, so there's a lot of blue that'll kind of overlap. My favorite class, though, is the horse class. Because if you look at the horse weights, it does you can kind of see a horse head a little bit here, and you see one here, too. So this looks kind of like a two-headed horse. And the reason is because many images of horses show a horse from the side, and it's either facing left or it's facing right. So the average has a little bit of both, and it's kind of trying to hedge its bets to be able to find both. Right? Now this is kind of a good segue into understanding what hidden layers of neurons can do. Right? So neural networks, when we looked at these weights, this is just when we have one, there's no hidden layer here, right? But oftentimes, and we can kind of look at a forward pass here. So, but usually we'll have hidden layers. Now, why would we, this is a good, the horse example is a good example of how a hidden layer could be useful. And I'll show it once the network loads. I hope this is working too. Okay, good, it's training. So, what do hidden layers give us? So if we look at, okay, so this is a neural network which is taking these CFAR samples. This is a typo actually. It should say pixel 3072 because CFAR images are 32 by 32, so they have 1024 pixels, but they also have an RGB. So really we have 3072 inputs that's going in here. And then we have a middle layer of neurons, and then the final output layer has one neuron for each class. And this one is actually correct. This is it's a cat. This is an image of a cat, if you can tell. And the cat score appears to be the highest. Although you can see there's a lot of confusion. It's confused a little bit with dogs. We can look at maybe a few more of these. So that's a ship. Did pretty well. 2 out of 2, not bad. Ship, another one. This one is I can't even tell. Oh, it is an airplane, but it looks like it thought it was a ship. It's actually doing surprisingly well. Yeah, here we go. This one's an automobile, but it thought it was a cat or a dog. Okay, so we can see. So anyway, what's it doing here? Well, we can kind of work backwards to get a sense of how the hidden layers work. So before we went straight inputs to outputs, right? And so we'd be able to learn these weight templates, right? But now into each output class, there's I think 15 hidden neurons. There's only 15 weights going into each of these. So now the template that's plugging into the output neurons has only 15 weights. It doesn't have weights for all of the pixels. It's just from these hidden neurons. So it's getting a lot less information in some sense, right? But it ends up working better. And the reason is because these hidden neurons are much more valuable than these pixels, because we've kind of learned a little bit along these connections first. And if that's a little abstract, it'll make more sense when we talk about the horse example. So again, let me just quickly pull up the MNIST weights. I should be doing this for CFAR, but just because my CFAR weights are broken. Imagine one of these were a horse class, right? It would learn, if we were doing this for CFAR, it would basically learn something like this for the horse class. right? One of these would be the horse, right? And we should recognize that it's a disadvantage to kind of use something like this, because if we get a left-facing horse, it's not going to line up very much with this right here, right? And if we get a right-facing horse, it won't line up very much with this. But if we have a hidden layer, then imagine the horse class could work something like this. We have this hidden layer plugging into the horse class, and suppose it were the case that left-facing horses achieved a very high score for one of these hidden neurons. Like, let's say this one right here. This one is a hidden neuron which scores highly for left-facing horses, and maybe this one right here scores very highly for right-facing horses. And all of these others don't score highly at all for horses. That's good, because then this horse neuron could have a high weight connection between the right-facing horse hidden neuron and the left-facing horse hidden neuron. And then it would have a low one for all of these others. And so then these hidden neurons, the connection between the hidden neurons and the output layer, it almost functions like an OR function. It'll be like it'll have a high score for either left-facing horses or high-facing horses, but then all of these others, they don't have the weight plugging in from this neuron and this neuron to horse is only going to horse. It's not going to the other classes. They have their own weights, right? So we can, in principle, use the hidden layers to learn different kinds of horses, and then we combine those in the final horse classifier. Does that make sense? I know that's probably a very sort of what they say is hand-wavy explanation, but it's kind of like the best I can do without a demo. This might be a little more clear when we start using when I show you the demos. But for now, like if that's confusing, think of just imagine this. We can learn different kinds of horses in the middle layer, and we can learn different kinds of cars and different kinds of different kinds of dogs and so on. And then we can use those we can combine those within the final classifiers. So there's sort of this two-step process. In reality, really, it doesn't quite end up working that way. Like we can think of that's a way that the neural network could learn, but usually it ends up learning sort of more abstract features in the hidden layers. So like, for example, like dogs, cats, and horses might all have some things in common. They might all have a body which is mostly brown colored in the middle of some clutter, right? So they might all kind of learn that abstraction first, and that might be one of the hidden neurons, and so it will have a high weight for all of those, so for deer, dogs, and cats. But it will have it will plug in, that hidden neuron will have a low weight for airplanes and ships because they don't tend to have that. So we're kind of learning like this sort of compositionality, and that's really what happens in neural networks, is that we are progressively learning higher level abstractions at each layer. So in the first layer, we just have pixels, raw pixels. In the second layer, we might have these kinds of things like, okay, animal surrounded by clutter, or one of these neurons might be something surrounded by blue because it's in ship or water. And then these output neurons become a function just of those abstractions. And the abstractions are learned specific to that training set, so they're useful to this particular data set. But they're sort of more meaningful to us also, because they have these sort of abstractions. And if we have more layers, then let's say we had 5 hidden layers. Then we're giving the network an opportunity to learn more slowly. So it can learn like an initial set of abstractions, which are just like super, very hardly disconnected from the pixels. Maybe like it might learn I'll skip this because this is actually what convolutional neural networks do really, really well, and that'll become more obvious when we see the more layers. But just for now, like, imagine the idea that hidden layers allow us to learn abstract features that eventually become more meaningful both to the machine and to us also. With the final layer being the classification layer. Okay, so let me just quickly look at the notes. Okay, so let's look at convolutional neural networks. Okay, so this is a demo. So I'm actually going to show you this demo. I have it online. I don't think I've actually posted it online yet. I'll do that today, but I'll just show you my local copy. Okay, so let me just quickly leave this be. Okay, so first of all, the first important thing to understand about convolutional neural networks is that they are a special type of neural network in that everything that we've learned about neural networks applies to convolutional neural networks. Convolutional neural networks, and just to save breath, I'm just going to call them Convnets from now on. You'll hear that a lot. People say Convnets. Sometimes CNNs, convolutional neural network, are just shorthands, but I'm just going to say Convnets. So Convnets they basically improve neural networks by adding a couple of different innovations to them. So everything that we know about neural networks applies to convolutional neural networks, but the main innovation is that they have two added layers, or two special kinds of layers that don't exist in ordinary neural networks. So the kinds of layers that we see in ordinary neural networks, where you have where the weights are connected like this, they exist also in convolutional neural networks, in Convnets. But we have another kind of layer called the convolutional layer, which I'm going to describe how that works. In Convnet parlance, we call these fully connected layers. So this layer right here is called a fully connected layer, and it's called fully connected because all of the neurons in the layer that precedes it are connected to all of the neurons in what's called a fully connected layer. In convolutional neural networks, we're going to break this assumption, and we're going to have non-fully connected layers, and in a particularly elegant way, which will make sense when we kind of have gone through the whole pipeline. So let's look at it, right? So yeah, there's two different kinds of layers which I'm going to introduce: convolutional layers and pooling layers. Pooling layers are, and I'll introduce pooling after convolution. Pooling is actually really simple. It'll take like 1 minute to describe. It's basically downsampling. But convolution, that's a little bit more involved. So I made a demo to show how it works. So recall that when we take these pixels in the view of an ordinary neural network, we kind of unroll them into neurons, right? So that's our input, right? So in this view right here, actually, you know what would be nice? I'm going to let's split screen this. Yeah, perfect. So all of these pixels in this image of a 7, right? And we have other images, right? These are all images that come from MNIST. These pixels in the regular neural network are these pixels right here, and there's 784 of them because it's 28 by 28. And then in the second layer of neurons, the next layer in the pooling layer, in the convolution layer, is these, right? So basically, instead of going from these pixels to these 10 neurons, we're going to go from these pixels, the same, to these right here. So here there are actually, there's 22 of these, I think, 22 by 22. So there's 484 neurons here. So it would be like, we're learning a hidden layer of 484 neurons coming from this. And this is how it works. This is how it's done. Basically, instead of having one huge weight template that gets applied to this whole thing, we have a bunch of little ones that we slide across the entire image. All right, let me back up. Let me start over. I'll start with one filter. Okay, so this right here that we're looking at, this box, is a weight filter. We call them filters. Sometimes you'll hear them called kernels, but it's basically weights, right? And these weights are analogous to these weights right here, but they're much smaller. So these weights are the same size as the pixel, the images. They're 28 by 28, but this one is only 5 by 5. So it's not even the same size as the input. And the way it works is that we take the original input image, and we grab this filter, and we slide it across basically across the entire image, every row and column. That's us doing that right here. And you can see that this green box right here, it's just zooming in. We're zooming in on every subset, right? We're zooming in on every 5 by 5 subset. Yeah?
Is that offset like for each row and every column?
Yeah, so in this demo it is, but it doesn't have to be. For our purposes today, you can just assume it's every one. There is a parameter in Convnets called stride, which tells you how you can skip. Sometimes it might skip, basically, and might go every 2. But for this demo, it's just every row. So the stride is 1. And the size of the filter is also not.
Are there biases in Convnets?
Biases? Oh, yes, there are. Yeah.
Like, because I imagine the filter are, like you mentioned, are the weight. Is there a way to like visualize what a bias would be with this filter, or like, or?
Sure. We could. I don't have it. I don't have the biases visualized here, but every neuron does have a bias. Yeah. I haven't been talking very much about bias because for our purposes, it's not necessarily super important. But remember that each of these neurons has a final value that you add at the end. But it's sort of, for our purposes, not very insightful because we're interested more in weights, because weights tell us what the neural network is seeing. So that's kind of, there's an end game here, which is to understand what they see, and that you gain more insight from the weights. But yeah, but to answer your question, yes, there are biases. So each of these has a bias. So we slide this across, right, and we get these subsets, and then the way that the operation works is that this subset, which you see inside the green rectangle, we take the dot product of it and the filter. So you see that we take this and we multiply element by element. I wish I could stop this, actually, but I don't have it set up. Yeah, because I want to use my mouse, but when I leave the mouse, it starts going automatically. So this is one of those coder problems. You forget simple things. But basically, it would be an element by element multiplication. So this times this, plus this times this, plus this times this, and so on. So there'd be 25 multiplications, and then they get all added together. So in other words, it's the exact same operation that happens here, too. Right? These are all pixel times weight, plus pixel times weight, plus pixel times weight. Right? It's the same exact operation, except it's done in a very small subset of the image.
It's like this filter is
The filter has a series of weights, so it has 25 weights. Right? So now you can understand why we call this a fully connected layer and this is not. Because in the regular neural network, we're doing the same thing, but we just have one big filter, and we don't slide it. It's just one big filter that gets multiplied weight times pixel, and then that becomes your output neuron.
Did you do this with 8 different filters? No,
Yeah, right, and I'll get to that in a second. But let's first finish the first filter, and then we'll see why there's 8. So yeah, this is a filter that gets multiplied. And so now, and the result is, for each one, you get one value, which is in the red box, right? So when we multiply, when we take the dot product of this and this, it gives us one value, this, and then that becomes, you can see that I highlighted in the red here. So as we move it across, each green subset is associated with that one red pixel. Does that make sense so far? Okay, so now we'll talk about why the filter appears the way it does. So this is the response. And maybe we can look at a few more of these. So like, you can see that they vaguely look like the input image. But some pixels are higher than others. Now, why are some pixels high and some are not? Well, we'll use this 0 actually to describe. Actually, let me use a different filter also, because I think some of them might be. Okay, yeah. Let's use this one. Okay, so intuitively we can see that the response is higher for some regions and lower for others. Why would an image? Maybe someone can volunteer to an interpretation of like why some are higher than others. So like, for example, this right here is pretty high. If we look at the subset of the image and the weight, this particular dot product is high, whereas this one is low. So why is this one low and this one is high?
I mean, it's 1 is 0, and when you multiply it,
Right.
I mean, like,
I think it's a feature, it's feature, it's just feature, right? So if it's kind of close, it's getting more square, it's opposite to something
Mm-hmm. Right? Yeah. You had also.
Just the closer that the little sample matches up to the filter, the higher the value you're going to get.
I mean,
Exactly. Yeah.
in my math, it's because like the black multiplied with black is going to be 0, but then if you see there's going to be a lot of whites because like ones.
Right. Exactly. Yeah. So in other words, it's still more or less what we saw before in the fully connected layers. You'll get a high score when the subset image is very similar to the weight image, because they're sort of like they resemble each other. So this right here, you see there's like a lot of white in the bottom right corner, and so it looks very much like the filter. And so when we do the dot product, the blacks will cancel out with each other basically. Like it'll just be 0 times 0, so not very much score. But you'll get a lot of high score coming from multiplying white times white. So you'll get a very high score. Whereas when we move this down right over here, now you're seeing this has a very low score because all of the whites in the filter image are getting just killed by the dark weights. And then the high weights, they don't have anything to be multiplied by. So this just they sort of cancel out. Or not cancel out, but it's sort of like wasted weights.
It's like inverse.
Exactly, yeah. So in other words, like these filters are more or less lighting up high when it finds parts of the image which are sympathetic to it. So it's looking for sympathetic patterns. So in other words, it's very much like an edge detector. And actually, like in computer vision, you use a very similar process. Like if you do. And not just with computer vision, but just like most image processing deals with like for example, if you do a blur, it's just applying a filter, like a multi-pixel filter, and it's looking for sympathetic patterns. Or blur is not looking for anything, but but an edge detector, like a
Difference of conscience.
Sorry.
Difference of conscience.
That could be sure. Yeah, that would be one. But yeah, they're basically edge detectors. They're not exactly edge detectors, but they end up looking very similar to edge detectors in practice because edges tend to be useful. But really it could be anything, right? And sometimes some of these weights might be sort of more like a gradient or so on and so on. one question that you might be wondering is why do the filters look the way they do? Like, why do we have this set of filters and not some others? And I'll get to that. I'll get to that later. But basically, it's the same as neural networks. They're learned. So, and we'll talk about why it learns these particular ones. But yeah, this filter is pretty good. So you see, it's pretty high. So yeah, if we look at the response of this 6, we see that it has a lot of high value on the sort of like left edges, right? Because it finds a lot of like on the where you get like from going left to right, you get a dark to bright transition, which is along the outside of all of these of the 6. You get a lot of high values, and then you get the exact opposite on the right side, on the right edges, right? Because here you have bright to dark, which is the exact opposite of that filter. So this filter is essentially, it's sort of like a left edge filter.
Is that image on the right just like the dot products of that filter in the image, or all filters combined?
It's just that filter, yeah. So yeah, just to review, every element in this filter is the result of one dot product. So for example, if I put the box here, we take this image X, take the dot product with the filter, and that becomes that one pixel in the red. So that's one response. And there are, in this particular convolutional neural network, in this layer, there are 8 filters, and so here's all of them. And so you can see the response for each one varies. And we can kind of interpret each one. So like this one, some of them are a little harder to interpret than others, like they may not necessarily be edge detectors. This one, okay, so like this one will light up when there's a lot of high value in the in the top half. Yeah, this one is pretty good because it looks kind of like an edge. But
each feedbacks have each rate.
Sorry.
Has each rate, because I think this feeder is used some way this rate, right? And if this rate is 6, if you apply this feeder, you can get more, like 6 looks like images at the end, right?
What do you mean?
Like if you use this feeder,
Yeah.
4.
Yeah, if we look at different inputs, they'll always usually look, you see like different,
Okay.
right? They'll always, like that filter, the response will look, like it's highlighting certain parts of the original image. So they're sort of like edge detectors. Like if we look at the filter that we looked at before, this one, you'll see that it's basically finding left to right edges in every, right? You see a lot of left to right edges. So leftmost edges. If it were the opposite, if like the white were on the other side, then you would have right side edges light up. So the function of these filters is to basically find different edges. At least in this layer, it's to find different edges. This will become more abstract in a few minutes, but at least in the first layer, you can kind of interpret it that way. Yep.
So would the filters be like 8, 25 encrypted layers that are parallel to each other?
Sorry, with
I'm
the
trying to visualize it in the same way that we have the neural network over here.
right.
How is that broken up in terms of ideas of like hidden layers,
Mhm.
inputs and outputs?
Well, if you wanted to plot it in sort of this way, then this is the way you could go from this to this. Basically, there are 10 neurons here. First of all, forget about all these, like pretend they're not there. In this one, we just have 10 neurons, but here instead, now there'd be 484 of these. Right? There's each of these pixels, basically, all of these pixels in the response, it's a little more complicated. But just imagine, let's start with this. Like all of these would become a neuron here. And then And then the connection to this one would be basically coming from 25. There would be 25 connections to it from just some pixels. These inputs would still be the same. It's still the original image. But then connecting to this one right here. So if we look here, right, it's like pixel 1, pixel 2, pixel 3, pixel 4, pixel 5, and then pixel, what would that be? That would be 28, 29, 30, right? It would be like these first 5 and then another 5 down here. They'd be 25 in total connecting to it, and all of them would have some subset of the pixels. But I usually find it's for me it resonates more to look at it from this view, because then you can see what they're looking for basically. So now that what I just described is only assuming that there's one filter. In reality, there's more filters, and I'm going to describe when we do the full demo. I'll describe how they plug in. So yeah, you get all of these. So you get an input, and you get these. There'd be 8 responses for each input, right? So each filter gives us 8 responses. You might be wondering why 8. It's arbitrary. Like this particular network has 8. It's just something that we'll get more into network design later, or maybe not. We probably won't cover that too much detail. But basically, it's arbitrary. We just look for what works best. Okay, so that's basically the first layer, right? Now, so this is what a convolutional layer does, right? There's also a pooling layer. What a pooling layer does is it goes from these neurons right here. So suppose we had some hidden layer of neurons that looks like these. All pooling does is it downsamples. So it would take, usually we use max pooling, which means it takes every group of like 4 pixels, usually 4. So it'll take like these 4 pixels, take the max value, and turn it into 1 pixel. So these 4 would become 1 pixel, these 4 would become 1 pixel, these 4 would become 1 pixel, and so on. So all it does is it reduces it from 484 pixels to, what would that be? That would be 121. So because it downsamples by a factor of 2 in each dimension. So pooling is really simple. It's just downsample.
Why max and not average?
So actually there are also average pooling, and max pooling was found experimentally to perform better. Which is kind of, it is to me also, because you think of maxes as destroying information, but for some reason it works better. Actually, what's happening now in the research is now they're getting rid of pooling layers altogether.
I think if you use max values, you get like a narrow range of values, but you get more difference when you use average and like.
Oh yeah, it might be too similar.
Yeah.
Could be, yeah.
Would max and min be just as effective?
Well, you
It's like-
probably don't want to use min, because that would be, then you'd be looking like you want max because you're looking for features. You're trying to detect features. But max, for whatever reason, they found that max works better because they're interested in finding the feature regardless of where, if there's a little bit of wiggle room, they just want to know that it's there. But average pooling was experimentally used also. These days now, pooling layers are being, there are experiments that have used all convolutional layers, and they actually reduce the pixels by using strides. So what we talked about, if we were to skip these, right, by 2, instead of going by each one, then we'd also have half as many pixels. So that's another way to downsample. And they're finding that actually seems to be in the future, maybe we'll be getting rid of pooling layers altogether. So yeah, very fast moving field. Actually, even faster, is now there's talk about doing totally binary, which is, I don't know. We'll see. By next year, this might all look completely different. You can see why I'm making this up as every week, because if I prepared this 6 weeks ago, it would have been obsolete by now. Yeah. That's exaggerating, but so we have these responses. Okay. Now what? So I described pooling, but really the convolution is sort of the main thing. And now what I'm actually going to do is I'm going to open up a demo, which I have in here. Okay, so now I showed you this in the first week. Now we're going to see this a little more carefully. Okay, so basically this is the image. Now in this, the one that I showed you was kind of a toy network. This network right now, I've got a saved model of a network which is trained to perform very accurate 1,000 class image classification. So this is a really good network. And in the first layer, it actually, instead of having 8 filters, it has 96. So these are all the responses. And we can look at the weights also. So these are the weights right here. They're color weights. So just to make sure we understand how color would work, if there was color, then I don't have a demo for this just now, so just use your imagination. Imagine that our 3 color channels, it was there's 3 of these, and they're kind of stacked in the plane. They're like a stack of them. There's 3 of these now. And so instead of being a surface, it's a volume. So you can think of it as a volume, and there's 3 of them. And so then the filters would also have 3, there'd be 3 layers to them. And then the multiplication, the dot product would work just the same. It would work element by element, layer by layer. So then instead of having 5 times 5, 25 multiplications, there'd be 75 multiplications. And then this would still be grayscale, right? Because it would be, you'd get a single filter, which is that you're condensing all of the channels into one. But what's interesting is that because there's multiple filters, you combine. Sorry, let's go back to the demo before I confuse you more. Okay, so we have these filters, right? These color filters that go through. Let's use this. Much better.
How are the filters generated?
The filters are generated through training, and I'll describe that. They're basically remember that neural networks are trained to minimize some, or to maximize something that we want to optimize, right? So if it's trying to optimize classification accuracy in some training set, it will determine weights which are helpful for that. And in the first layer, that tends to be things like edges filters, right? But they're learned. They're completely learned. And so it learned these edges. And so we multiply by each of them. And so the first filter right here corresponds to this right here. So we took this filter, this first one in the top left. How much time do I have? We are going, probably gonna, I'll have to.
Real quick, if you were using the live feed, would those filters be evolving as well?
The filters stay fixed. Yeah, the actual weights, they're trained, and then they just stay. Only the response is changing. So this is the result of taking that first filter, sliding it across this image of a dog. And so you see it kind of lights up for right edges, roughly speaking. Whereas this one lights up for sort of horizontal edges. But they're not always edges, right? So this one right here, it looks to me, and we can try to figure this out. This one is the 30, so this is 32nd filter. So it corresponds to, there's 4, 12, 36. I think it's this one right here. So this one, I should also mention, this is all dark, right? So you'd think that they should all look kind of dark, but it gets normalized. So basically, this looks to me like it's looking for consistent surfaces. So if there's consistency in the surface, that's the way I'd sort of interpret it. You'd get patches which light up. So it'll kind of go darker around the edges, I think. That's my interpretation. But basically, all of these are the result of these responses. I just want to, just because we're running a bit late, I want to really quickly look at the schedule and just decide what we're going to have to reserve for next week. So I want to go through this whole demo, and then basically I guess we're just going to have to talk about applications next week. So we'll start doing this stuff next week. So today we'll just finish the demo, and then we'll start talking about what to do with them. Okay, so we have these responses, and then I didn't talk about this, but this is really simple. It's just normalization. So basically, makes all of whatever the most white is, it makes them all and normalize them. So to go from this to this, it's normalization, and then the pooling, it downsamples. So they look like they're the same size, but I'm just drawing them the same size. The pixels are now twice as big. So this is sort of one round of this convolutional neural networks to generate these responses. Now it may not be obvious why these are useful, but it will be once we've run through the entire simulation, right? So what happens in the next layer is that we do another convolution, right? Now this time, there's another set of weights. I don't have the weights. These are just the first layer weights. There's going to be another set of weights, but they're not really useful to look at anymore because they're not as easy to interpret. So if we do another convolution on now these right here, the first thing to understand is the way we do it is that we take all of these responses and we compress them together into one big volume. So it's kind of like before where we had a red, green, blue. That was a depth of 3 volume. This volume has a depth of 96, I think, yeah? And then the weights also have a depth of 96. So there will be a set of weights that will get, again, multiplied bit by bit, every element by every element, like the x in the x dimension, the y dimension, and in the depth, and then turned into these responses right here. Now these are much more difficult to interpret, but they're kind of similar, right? They're looking for, you can see the faint outline of the dog, but the way to interpret what gets highlighted white and what doesn't is like is that it's basically analogous to these with respect to the original image, that it's basically looking for, maybe a good way to describe it is like edges of edges, sort of. So like if some of these have a particular kind of response, right, some regions of this volume, and a particular weight is looking for this combination of edges. You know, like you might have some edges and different kinds of edges in close proximity with each other, and some of these weights in the second convolution are looking for these. And then they will respond highly to that. It's really, I know that's a super duper, it's probably the most hand-wavy explanation of anything you've heard all year, I think. And it's kind of the best we can do. Once you've seen these enough times, it will begin to kind of, you'll begin to kind of understand it. Although, if you don't understand it all, hopefully you'll feel better knowing that nobody really understands them to a certain, like if you'll hear like researchers describe like, okay, they understand all the math, but the intuition is sort of escapes them. And so we just have to deal with that. The best way to understand is that these are looking for now higher, they respond for higher level objects.
It's like a Wekinator feature of
Features of features, yeah, sure. In any case, we do this again, the local response, and then we pool. So now we've reduced the size of these pixels by a lot, right? Then we do another convolution, and this time these convolutions for this particular network, the way it was set up, I think these have, I forget, I think these might actually have a stride of 2 because there's no pooling. And then when we get down here, you hardly see the dog at all, but the dog is still there, right? But these these features, and let's actually just go to the pooling. So this is the final layer before we get to fully connected layers, and these are lighting up in a certain way. Now these are hard to interpret, but one time, and I did this in the first class, but like I tried to find one that looked like it was only white for the face of the dog. So maybe it's this one. I think some of them are a little stronger. This one, let's say, I think it's only, and actually, let's turn the webcam back on. So now this is doing live encoding, and one of these should respond well for maybe it's this one. No, not really.
You have to find it.
We don't have to find it, but 32. Which one?
One down, and one left.
What?
This one right here.
I mean the bottom.
This one right here?
Down.
Maybe this one.
Yeah.
Hard to say. The point is, imagine it was though. Imagine it was. One of these might be looking for human faces. It looks different sometimes I have trouble finding it. But what's interesting is, you know, like some of these will light up also for the face, but they might light up for, like one of these might be also lighting up for my face and hands. So it might be like a skin detector. So basically, instead of finding edges, it's finding abstract features. And we didn't tell it to look for faces, like we didn't build a face classifier. It just determined that this particular data set, which has a lot of objects that have faces in them that we want to be able to discriminate amongst, it found features that would necessarily find faces, basically, because faces tend to be useful for making this classification, as do other things, right? So all of these, and a lot of these are just hard to interpret altogether. Like they might respond for things that there's actually a really good video about this, and I'll share the link with you guys later, where some of the first people to work with visualization made an actual application just like this one, basically. This one is more or less modeled after that one, and they describe different kinds of features that you can find. Like one they found was like a wrinkle detector. So one looked as though it was responding to clothing, but it was really just responding to wrinkles. Another one was responding to text in books, because it was useful for determining that something was a book. So it would light up for text, but not for other things. So that's pretty interesting. Like it'll find sort of high level things. So at the end, you have all of these, right? These are all neurons. You take all of these and you make it into one big row, and then you connect it to a fully connected layer. So all of these go into a fully connected layer, just like one of these, right? So this is a fully connected layer. At the end, and this is almost very common to do with convolutional neural networks, is to have one or two, usually two fully connected layers at the end. So this is a fully connected layer which has, I think it has 4,096 neurons, and I have them in the horizontal format, but really it's analogous to this, right? It's just you can take them all and unroll them and stretch them, right? And this is the second to last hidden layer, and then this is the last hidden fully connected layer. And forget these classifications for just a second. We already saw these, but one thing to notice about these is look how persistent they are, even as I move, right? Usually when we do like edge detection, things like that, these they're very vulnerable, sensitive to movements or adjustments in lighting and things like that. But these are actually much more consistent. They do change and light up to some degree, but you'll see that certain ones, like this neuron right here, looks like it's just staying there, basically, even as I move. And the reason is a property of convolutional neural networks is that they are much more resistant to changes in these low-level features like lighting, or and they're very good at and this is partially where the pooling is useful. The pooling down samples and kind of gets rid of like pixel to pixel variance, and so this is it stays, the feature vector stays much more consistent and is much more a function of these high level things that it's discovered. And then finally it goes into one more layer, which is in this particular network is the classification layer. So this network was trained on 1,000 classes. I think it's ImageNet, might be something else, but it's trained on to classify 1,000 classes, and so these are it, right? And we're actually just looking at the top, whatever this is, top 20 or something. So like if I put my phone in front of it, it should find iPod as one of the classes. So it's pretty good at finding. I think the reflection is kind of screwing it up. iPod, and then also, like if you, maybe the remote control. We can try like different things. Cellular telephone, crossword puzzle. Okay, remote control. Kind of impressive. We tried this with the laptop before. We tried shoes, I think. But basically, like it'll work to the extent that you show it things that it recognizes, and it's a pretty good classifier, right? So and despite all of the clutter in the image and all these other things, it found the features that make up a phone. You know, maybe it found screen and edges, borders. Maybe the button might even be detected somewhere, and so it does. A pretty good job of classifying. So it's just about I showed you this before. It classified my face as a wig. So just because it's the end, all right. So just give me 1 minute to kind of just wrap things up. So basically, okay. So what we did was we just went through a demo of a convolutional neural network, and we got a basic sense of how it works. What I'll do is I'll send you some links tonight for that might clarify some of these, and some people who have done maybe a better job describing these than I have. That should hopefully make these apparent. If you're like really struggling to understand the low-level details of this, I commend you, because that's something we should all strive to do. But understand that like it is necessarily abstract. It took us like decades to figure it out, even. So it's well enough for most of our purposes to understand this notion of compositionality and high-level features. If you understand that to some degree, then you should be good to understand when we start to make applications of these. So, in terms of understanding these volumes and like precisely how the multiplications work, definitely like it's not super critical. Next week will be really fun because we're going to show all of the really amazing things that these do, because it's not just this classification that's really interesting. It's that the features themselves, because they're determining high-level features, they have lots of ancillary applications that we can use them for, and we'll start to show those, and we'll talk about deep learning more generally next week, and hopefully get into setting some of that stuff up. Okay, so are there any questions? Last-minute questions? Just in terms of assignment, the assignment this week is the same as last week. So some of the critical reading stuff that we did, if you want to volunteer to show something, please do. Otherwise, think about making a Wekinator, maybe developing some more Wekinator applications. And then next week we'll start to show some of the deep learning libraries, I hope. And then maybe that will lead to some other cool application areas. And I'll send you guys some links in the mail. So I guess that's about all. Okay, cool. For anyone who's interested, I'm giving a presentation right now at Baby Castles, which I know is a big, should be, I think, a lot of ITV stuff happens there. Tiga Brain will also be there, good friend. So yeah, but I don't think I'll be talking about this, actually. So yeah, if there's any questions, I'll hang back for a little while. Otherwise, I'll see you guys next week. So thanks.
I saw you know Ranjit here in Harlem.
I